večer. Moje meno je Michal Zajaček, som z Masarykovej univerzity z Ústavu teoretickej fyziky a astrofyziky. A je mi cťou predstaviť dnešného rečníka, profesora Bharata Ratru z Kansas State University. A keďže profesor Ratra je očividne zo Spojených štátov, tak prednáška bude v angličtine a následne v časti tej druhej, ak budú nejaké otázky do diskusie, tak samozrejme sa to budem pokúšať teda z angličtiny prípadne nejakým spôsobom, alebo do angličtiny prekladať a nejakým spôsobom tú diskusiu moderovať. So, good evening everybody. It's my pleasure to welcome our speaker today, special guest, Professor Bharat Ratra, distinguished professor from the Kansas State University. And it's really nice that Bharat had opportunity to visit Brno. We started to collaborate on some work in cosmology actually during the pandemic, and we mostly communicated online all the time via email, so it's now really nice to meet Bharat in person after a year or two. And Bharat prepared for us a really relevant talk nowadays on the accelerating, expanding universe, on dark matter, dark energy, and Einstein's cosmological constant. So I think it's now the best to give a word to Bharat to continue with his talk, and later in the second part, so after 1 hour, then we will have space for your questions and discussions. So please, Bharat.
Thank you very much, Mikhail. It's a great pleasure to be here and finally see you in person. Before I start, I just wanted to point this web page out. You should have these cards, and it's a really nice site if you're interested in understanding global warming. So I'm a cosmologist, and that means I'm interested in studying the structure of the universe and the structure of contents in the universe and how that evolves in time. And this is a really nice time to be doing that. You've probably all heard of the James Webb Telescope. There's lots of other new telescopes, both on the ground and in space, that are much more sensitive than in the past, and they're collecting a lot of interesting data. And these data are reinforcing two very, very interesting results that have been around for maybe the last few decades. One, I think that you've all probably heard about. When we look at the energy budget of the universe now and look at what makes it up, we know that atoms and molecules, the kind of stuff we're familiar with, contributes only about 5%. The remaining 95% is made up of some unknown substances, and we have no idea what they are. We're seeing the gravitational effects of these two things that we call dark matter and dark energy, but we don't know what they are. So there's a lot of interesting work to be done to discover most of the contents of the universe now. The other thing that's really interesting is that these cosmology observations are suggesting that either quantum mechanics or Einstein's theory of relativity, or perhaps both of them, are incomplete descriptions of reality, and that they might both need to be modified. And that would be really, really interesting, because both quantum mechanics and relativity have been at the foundations of physics for more than a century now. So I live in Kansas, and there's a lot of prairie there, which is grassland, and these are American bison. These are not cattle. And this is about 10 minutes away from where I live, and it's a nice place to go hiking. So I have a couple of questions for people in the audience. You can put up your hands if you can answer positively. How many of you have gone hiking 10 kilometers in your whole life? Okay, what about 100 kilometers in your whole life? 1,000 kilometers in your whole life? Okay, one hand. 10,000, two hands. 10,000 kilometers. Okay, so there's an upper limit to how far you can go. I guess if you're really patient and you spend a lot of time walking, you can go pretty far. So I want you to reach up and grab a strand of your hair and feel it with your fingers. And just grab a strand of your hair. So do you think your fingers are fine enough, have fine enough sense to feel something narrower than your hair? Or is that kind of the limit? It's somewhere around there, and that's about maybe 100 micron or so, maybe 10 to the minus 4 of a meter. So there are kind of limits to what we can feel with our senses. And I've got a whole bunch of scales up here. So I'm doing this in meters. So 1 meter is a typical human scale. Maybe if you're very, very patient, you can walk out to 10 to the 5 meters in a long time. And if you have very fine fingers, you can feel down to 10 to the minus 4 meters. So those things, those length scales are directly accessible to your senses. But when you go down to much smaller length scales, you can't touch atoms, you can't touch molecules or quarks and leptons with your fingers. And the same thing's true on much, much larger scales. No matter what you do, you're not going to be able to go to much beyond the moon or maybe a nearby planet with a rocket. And there's still a lot of physics over here and a lot of physics over here. The physics over here was kind of established maybe in the 16th and 1700s and 1800s, especially by Newton. And you can kind of figure that out if you're very, very intelligent by rolling balls and colliding them together and measuring things that are directly accessible to your hands and your fingers. But the way you develop intuition on much, much smaller scales or much, much larger scales is very different, because you cannot directly access those with your senses. You need to use some kind of measuring device. So either a telescope, and you'll collect the light, and then you'll put that onto a CCD and turn it into electronic signal that you can process in your computer. And you've got to compare that, to predictions you make for models that you built mathematically on those scales. And the same thing's true down here. You can start out with microscopes, and then eventually you'll go to particle accelerators, but you're not going to touch electrons and you're not going to touch protons. You build mathematical models from quantum mechanics, and you predict what you see in those particle accelerators. So the way you build intuition here and the way you build intuition here and the way you build intuition here is very, very different. And maybe that's the reason people find that quantum mechanics and relativity are unintuitive, because you have to have some math there, and you build these mathematical models, and if they predict the right things, then you accept that as reality. And that's kind of different from just bouncing balls around over here. And it's kind of important to have some understanding of math if you want to do physics or cosmology or astrophysics. So people sometimes don't realize how large this set of length scales is. So I'm going to walk out and go, I'm going backwards. Go from human scales, and instead of the old system of units, the metric system, I'm going to use this guy as the unit. You probably recognize him. So we'll be talking about Einstein's as the length unit, and half an Einstein is roughly a meter. So I could do this in terms of his mass or his age and talk about time scales too, but we don't have enough time in this talk to do that, so I'm just going to focus on length scales. And this picture is a picture of Earth from space. It's only become possible in the last 6 or so decades. This is Madagascar, that's the Horn of Africa, that's the Indian Ocean or the Arabian Sea. And to get some idea of the scale over here, what you need to do is you need to go to a store and buy 6.5 million Einsteins. And you drill a hole from the South Pole to the North Pole, and you place your first Einstein at the South Pole, the next one on top, the next one on top. And if you have 6.5 million Einsteins, you'll cover the diameter of the Earth. So the Earth is about a factor of about 10 million bigger than human scale. you can go out to our nearest neighbor star, which is the sun, and to cover this, one way to think about it is you do the same thing. You pile up a whole bunch of Earths here from the North Pole to the South Pole, and you'd need 100 Earths to do that. Or if you want to do that in terms of Einsteins, you'd need about 70 million Einsteins. And you'd have to go up all the way with that. 700 million Einsteins. So it's a factor of 100 bigger than the Earth. And we can go out to larger scales. This is just one little star near us. And I'm going to go and put a few more numbers down here. So we know that the Earth orbits the sun in an approximately circular orbit. It's not quite circular. It's a little bit of an ellipse. But to a first approximation, we can approximate it as a circular orbit. And then the Earth-Sun distance of this average circular orbit is 1.5 into 10 to the 11 meters. So you're starting to get many, many powers of 10. And it becomes kind of inconvenient to use the meter when you're trying to talk about stuff that happens on the solar system scale. So people who study the solar system or other exoplanetary systems have new units of length. And one unit is pretty clear. It could be the radius of the Earth's average orbit around the sun. And that's called an AU, an astronomical unit. So one astronomical unit is 1.5 into 10 to the 11 meters. Another way to think about distances here is to think about cruise control. If you have a car and you set it at cruise control, it's going at constant speed. And if I want to go on a train from here to Vienna, I know it's maybe about 150 or 200 kilometers. If I go like 50 miles an hour, 50 kilometers an hour, it'll take me 3 hours. And we have an object that's perfected the art of cruise control, and that's the light waves. So light always travels at exactly the same speed in a vacuum, no matter where it's going, in what direction. And it travels at a really fast speed, 3 times 10 to the 8 meters per second. So you can kind of think about this as this is the one place where the foot is an interesting unit, because a meter has 3 feet in it. And so if you multiply, instead of using a meter, use feet. This is 1 billion meters per second, billion feet per second, or 1 foot per nanosecond. So light travels really, really fast. And so we can give the Earth-Sun distance in terms of this thing in meters divided by the speed in 3 times 10 to the 8 meters per second, and that's 500 seconds, because light travels exactly at the same speed. And so when you're looking at the sun, and you shouldn't look at the sun without protective equipment, but when you're looking at the sun, you're seeing light that left the surface of the sun 500 seconds ago, and it traveled in a straight line, and it hit your eye lens, and then hit your retina and got converted to an electronic signal, and that became the sun's image in your brain. So when we're looking at the sun, we're not seeing it the way it is right now. We're seeing it the way it was 500 seconds ago in the past. So we can go and step out even further. So the nearest star to the sun is in the Centauri, Alpha Centauri system. It's Proxima Centauri. And that's about a factor of 10 to the 5 further away than the sun is to the Earth. And in terms of AUs, it's 200,000 AUs from us. Or in terms of light travel time, light takes 4 years from Proxima Centauri to get to us. So when you look at Proxima Centauri through a telescope, you're seeing Proxima Centauri as it was 4 years ago in the past. You're not seeing it the way it is right now. If you want to see it the way it is right now, you'd have to wait 4 years, and that light that left it right now would reach you then. So it's becoming, again, pretty inconvenient to even use the AU when you're starting to study collections of stars. The AU is convenient when you're looking at collections of planets, but when you're doing stars, people start using a different unit, and that unit is the parsec. The abbreviation is PC, and it's a little bit of a strange unit, and there's a cartoon explanation of it here. So this came out of basically out of astrology, and that became astronomy, and then it got kind of standardized as a unit. But we have the Earth's orbit around the Sun, and the radius here that orbit subtends is 1 AU. And if you want to cover this in terms of suns, because it's 1.5 into 10 to the 11 meters, you'd have to pile up 100 suns in a row. So it's a really, really large distance compared to human scales. And this is not drawn to scale. But this radius here of this orbit is 1 AU. And if you take your observer and ask her to go far away enough so that this linear length here subtends an angle of 1 arcsecond at her, she's said to be a parsec away. Arcsecond is a very, very tiny angle. If you go around this whole circle, you have 360 degrees. And each degree you can split up into 60 arc minutes. And each arc minute you can split up into 60 arc seconds. So an arc second is a very, very tiny angle. And for such a large distance to subtend an arc second at the observer, that observer has to be really far away. And that distance is called the parsec. So if we were going to develop astrophysics and astronomy starting right now, we probably wouldn't be using the parsec as a distance unit. We'd use the light, the distance light travels in a year, which is sometimes called a light year, or you can say a year. And a parsec is roughly 3 1/4 light years. So this distance from here to here, when you subtend 1 arc second, is 3 1/4 light years. To give you some idea of various other length scales, the Earth-Moon distance, that's the furthest we've sent humans, is 4 × 10⁸ meters. And that's roughly 1 1/3 of a second. So when you see the moon, you're seeing it the way it was 1 1/3 second ago in the past. So if we want to use Pluto as sort of a characteristic scale for the universe, Pluto's orbit around the Sun, that's 40 AUs, or in terms of meters, it's 6 × 10⁻12 meters. On light travel time, it's 6 hours. So when you have a really big telescope and look at Pluto, you're looking at it was 6 hours ago in the past. The furthest humans have sent anything are the 2 Voyager missions. And these numbers, these guys were launched in 1977. They're still traveling. And the numbers I've given you here are from 2017. That's the 40th anniversary. So at that point, Voyager 1 had gone 140 AUs. Or in terms of light travel time, it's 19 1/3 hours. So when they send the signals back from Voyager, it takes 19 1/3 hours for it to reach the Deep Space Network receivers on Earth. And that's really tiny in terms of parsecs. It's a fraction of the distance to the nearest star. So even like in the solar system, we have these huge, huge length scales. We can go out further. And this is a really, really nice picture. It's put together from inside looking out. This is our Milky Way Galaxy. And if you go out of town, you could probably see it. And those of you who haven't seen it should try to look at it. This is probably much better seen on a computer screen, and there are many different versions of it. You can search for this on Google. It's the European Southern Observatory Milky Way Galaxy, or the ESO Milky Way Galaxy. And let me just go to an artist's impression of this. That's an old one from the past, so you can see how much it's improved. And this is an artist's impression. So what it is, it's like a disc, like a plate, when you're looking at it from the top. And it's kind of got a bulge in the center. So the disc is like this, and there's a bulge in the center. And let's start out with the scale here. So this is a collection of stars, roughly maybe 200 billion stars. The sun is almost an average star. It's about twice as heavy as an average star. So this is a collection of 200 billion stars like the sun. They have mass, they're pulling on each other gravitationally, and the disk is, they're rotating in the disk. And they have more complex motion in the bulge here, in the central bulge. There's a black hole over here that's about 4 million times as massive as the sun. And the stars here bouncing around. So there's a central bulge, there's the disk, and the sun is 1/3 of the way out. So the diameter of the disk of the shiny stars is 50,000, so kilos 1,000, 50,000 parsecs. And I told you that 1 parsec is 3¼ light years. So if you want to turn this into light years or light travel time, you multiply the 50,000 by 3¼ and you get about 160,000 years. So if you could travel at the speed of light and you started at this end, it would take you 160,000 years to cross this. So you can compare that to 500 seconds between the Earth and the Sun, and about 6 hours to Pluto, and about a year, 4 years to Proxima Centauri. This is 160,000 years. And we can't travel at the speed of light because we have a mass. So the only things that can move at the speed of light are massless things. But if you could, it would take you 160,000 years to cross this. It's a huge, huge object, and it's got about 200 billion stars. It's also got this halo around here that's roughly 10 times the size. And this halo is thought to be where a lot of the dark matter is. And in this halo, there are these globular clusters. There's about a couple of hundred, maybe 200 that are known for the Milky Way. These are collections of hundreds of thousands to maybe up to 1 million stars. And they've been around a really long time, so they're pretty much spherical. And they orbit the center of the Milky Way, roughly. They orbit in the halo. And this black band here is not the absence of stars. What it's indicating is the presence of dust, little particles, silicates and things, some of the things that you vacuum up at home when you're cleaning your house if you use a vacuum cleaner or a broom. And what this dust is doing, there's stars embedded in it, but the dust is absorbing the starlight and scattering it. And so it's not coming to us, and so it's obscuring the light from the stars. But because the dust is absorbing energy, because it's absorbing the visible starlight, the dust heats up, and it either explodes or it re-emits that energy, and so it can stay relatively cool. And it re-emits it at much longer wavelengths than we can see with our eyes. And if we had infrared eyes, or you have an infrared telescope, and you looked at this black region, it would be very bright. So when you're looking at pictures of galaxies, those are the pictures you see with visible light. But you can go onto Google and look at galaxies in the infrared, or in the radio, or in gamma rays, or in X-rays, and they don't look like these beautiful disks. At least the spiral galaxies don't look like that. And they look very, very different. So this is Milky Way Galaxy. There's many, many, many galaxies like this. And this is Andromeda. And if you haven't seen Andromeda, you should be, you can try to go out to a dark spot and you'll be able to see it sometimes of the year. This is also a spiral galaxy. It's a little bit bigger than the Milky Way. It's about 60 kiloparsecs. So maybe 200,000 years to cross it if you travel at the speed of light. You can see the dust lanes here, and you can see the spiral arms. The spiral arms are where really bright baby stars are born. Those are the really heavy stars, and they shine much brighter than the average star. And these guys are 2 little dwarf galaxies that are in orbit around Andromeda. They're held in by Andromeda's gravitational field. The Earth has about 30 or 40 of these. Almost none of them are visible with the naked eye, except for the large and small Magellanic Clouds, which you can see in the southern hemisphere if you know where to look. So Andromeda is 750 kiloparsecs away from us. And if you want to turn that into light travel time, it's 2.5 million years. So when you're looking at Andromeda, you're looking at the light that left it 2.5 million years ago in the past, and that traveled in a straight line and hit your eye. And you can compare that to things like 500 seconds to the sun, and a second and 1/3 to the moon, or 6 hours to Pluto, or even the size of our Milky Way. It's 160,000 light years. This is 2.5 million from us. And that's kind of an interesting time. So that's when the first hominids showed up on Earth. So Lucy from Ethiopia, she apparently climbed up in a tree to sleep, to stay away from predators, and she fell out 3.25 million years ago and killed herself, apparently. But that's when hominids started showing up on Earth. So that's Andromeda. And some of these guys, they're galaxies, and galaxies are like people. Some of them like collecting together. They have big mass, and they pull on each other through the gravitational field, and they form clusters. And this is a famous cluster. It's a nearby one. It's called the Vogel Cluster. And the scale here is a few megaparsecs. M is for 1,000,000. Or in terms of light travel time, that's a few million parsecs. So you multiply that by 3.25 light years. And so we're talking about 6 or 7, or maybe 10 even light years. So to cross this at the speed of light, it'll take you 10 million years. And you can compare that to 500 seconds to the sun. This is a really, really huge object. They're pulling on each other gravitationally. And every single speck of light you can see here is a galaxy. These are not individual stars. So you can probably see at least 1,000 galaxies here. You can see nearby ones. You can see that some of them look like spirals. That's an elliptical. And each of these maybe 1,000 galaxies has maybe 200 billion stars. And each star is roughly the size of the sun. So this is a huge, huge, huge object. And we can keep going, and want to get out and try to look at an even larger patch of the sky. So what we're looking at here, let's go back to the Milky Way for a second. So because of this dust over here, if you want to see outside the Milky Way, we're a little bit above the plane, so it's clearer to look up here. And that's what I'm going to show you a picture of here. This is a picture of the northern galactic gap. So they set up a coordinate system called the galactic coordinates, and they put the North Pole up there, the South Pole down here, and the equator is around here. And so that's how you set up this coordinate system, and you're looking at the northern galactic gap. And this is almost the northern galactic pole right over here. That's the Coma cluster. But these were taken by Shane and Virtanen at the Lick Observatory, which is in the San Francisco Bay Area, up in the hills outside of San Jose. And this was before they had CCDs, so they'd take these big glass plates, put emulsion on it, and stick it at the focus of the telescope. And they didn't have laser scanners, they didn't have computers. So by hand, these guys sat there and figured out the angular positions of 400,000 galaxies by hand. So if any of you are students here and are upset about your homework, you can kind of think about this. So the scale here is 300 million parsecs, 300 megaparsecs. So in terms of light travel time, it takes about 1 billion years if you travel at the speed of light to cover this. So this is a pretty huge collection of matter. These are galaxies, and each of them has a couple of 100 billion stars. And you can see clusters like the Coma cluster, you can see other clusters. But if you look carefully, you can see 2 other structures. You can see what are called the voids, these darker regions, which have very, very few bright galaxies in them. And they're actually dark because they don't have bright galaxies. They're not dark because of obscuration by dust. And if you look at the edges of the voids, you can kind of see the filamentary structure. So there's 3 kinds of structures here. They're the voids, they're the filaments, and then the bright clusters. And if you want to think about this, you can kind of think about bubbles in your bathtub where you have a soap bubble bath. So the voids are like the interiors of the bubbles, and they have very few bright galaxies. The brighter galaxies tend to be on the surface of the bubbles. Where two bubbles come together, you have an enhancement where you have a line where they intersect, and those are the filaments. And then where the filaments kind of drain together, you get the bright clusters of galaxies. So this is kind of a pretty inhomogeneous, or at least an anisotropic distribution. And that's kind of a little bit of jargon. So when I say something is isotropic, that means I'm standing at one point and I'm looking around me in all directions, above me, below me, and to my right and to my left and in front of me and behind me. And you can do that in this room. You can look to your right and your left and you see different people. And if you look above you, you don't see people. So this room is very, very anisotropic. It's not isotropic. So this campus is anisotropic. You look in one direction, you see some building. You look in another direction, you see a different building. The surface of the Earth is anisotropic. You can look at it from above and you see oceans and you see land masses in some areas. The Milky Way, I mean even the solar system, the Milky Way is anisotropic. You look towards the center of the galaxy, you see an enhancement in the number of stars. You look in the opposite direction, you see much fewer stars. And the same thing's true on the scale of hundreds of millions of light years. You look over here, you see very few galaxies. You look over here, you see thousands of galaxies. So this is anisotropic. And you look in different directions, you see bumpiness, you see different things. The strange thing that happens is when you go a factor of 10 on larger scales, that goes away. And this is the largest scale structure that we can presently see. It's the afterglow of the Big Bang. It's the cosmic microwave background radiation. And this is data taken by the ESA Planck satellite. That was the third satellite to do this. And so what they're looking at is microwave radiation. If you have a microwave oven at home, that's the same kind of radiation. You can cook with that. And also sometimes police Doppler radar, when you get speeding tickets, that's microwaves. So it's longer wavelength than visible light. And you can build detectors to detect this. And so that's what the satellite took up. They took microwave detectors up there. So you have the satellite here, and it looked at the sky in all directions. So it's like looking at the interior of a big ball. And so to show you this, I've sliced the ball from the North Pole to the South Pole and opened it out and spread it out. So if you want to close this up, you take this edge and you fold it up and merge it with that edge, and you go inside the ball. And we're looking here at cold spots. These are the red ones, and the hot spots are the blue. So plumbers have this backwards blue wavelength light, which is shorter wavelength, is more energetic, and it's hotter than red wavelength light, which is longer wavelength light, and it's less energetic. And so they can, from the color, they can measure the temperature of the light. And the first thing you might want to ask is, what is the average temperature across the whole sky if you average this out? And if you do that, it's roughly 3 Kelvin. And the Kelvin is the absolute temperature scale. When you go to 0 Kelvin, the only thing left there is quantum mechanical zero-point fluctuations, but all other motion ceases. And room temperature is 300 Kelvin. So this is very, very, very cold. But the next thing, after you've established that the average here is roughly, it's about 2 3/4 Kelvin, you can then look at the bumpiness, the hot blue spots relative to the red cold spots. And when you do that, the difference is roughly 30 millionths of a Kelvin. So it's a really, really tiny difference. So if you divide, so a millionth of a Kelvin is a microkelvin. And so the difference between the red and blues are roughly 30 microkelvin over an average background of 3 Kelvin. So you divide 30 by 3, that's 10, and microkelvin is 10 to the minus 6. So the average, the delta T over T, the bumpiness, is 1 part in 10 to the 5, which is 0.001%. So when you look over here, and you look over here, and you look over here, the difference is 1 part in 10 to the 5. And when you go down to smaller scales, maybe a factor of 100 smaller, the difference is much, much bigger. You see lots here and hardly anything here. So these are two very, very, very important facts about the universe on small scales, local scales, like in our neighborhood, and by our neighborhood I mean scales up to 50 million light years or so. The distribution is anisotropic, it's bumpy, it looks different in different directions in space. But when you get above 50 or 100 million light years, on average the distribution becomes isotropic in space. And I'm not going to go into these two facts about the universe, but if you're interested, you can go to Google or some other search engine and look for the inflation model of the very early universe. And be sure that you only look at reputable sites like academic sites or Scientific American or Discover or Astronomy magazine, because there's a lot of crazy sites out there. And you can read about this inflation model and how people think it explains these two things. So inflation has not been established completely yet. I mean, all the predictions it makes, and so far none of them really contradict observational tests, but we don't know, we don't have enough measurements so far to really establish inflation in any sense. Okay, so this one is even more difficult to appreciate. On large scales, the universe is said to expand, and so it's kind of really useful to think about what this means. So if you have something that's expanding, that immediately implies that you've got a measuring device that's not expanding the same way. And so you can kind of think about what your measuring device is. You can kind of think of a meter stick. So you have a meter stick, and you have a mass. Well, yeah, okay, so maybe I'll just drop this when I need to. So you have a meter stick, so there's a bunch of forces that are relevant. So there's the gravitational force, and so the gravitational force, if you have a little mass here and a big mass, which is the Earth, and I don't support this little mass, it's going to be drawn towards the Earth, and because of the third law of motion, the Earth's going to be drawn towards it also. But the Earth's much more massive than that little guy that I dropped, so the Earth hardly moves while the little guy moves much more towards the Earth. And that's the gravitational force. It's an inverse square law force. So if you have two masses, they're going to pull on each other. It's an attractive force. And if I double the distance, because it's an inverse square law force, the force goes down by a factor of 4. If I triple the distance, it goes down by a factor of 9. That's 3 squared. The other force that's relevant on these scales is the electric and magnetic forces, or the electromagnetic forces. And it's easier to kind of just think of this as two charges. So you have, say, electrons, which are said to have negative charge, or you have protons that are said to have positive charge. And they both have charge and they have mass. So if you have two protons, the gravitational force is going to pull them together. And if you have two electrons, the gravitational force is going to pull them together. But there's the electromagnetic force, and the electromagnetic force doesn't just have an attractive part, it also has a repulsive part. So if you have two positive charges, the electromagnetic force pushes them apart. And if you have two negative charges, it pushes it apart. And if you have a positive and a negative charge, it attracts it. So electromagnetism will pull unlike charges together and push like charges apart. So if we take two protons, and okay, so I forgot to tell you, the Coulomb's force, the electric force between these two charges is also an inverse square law force. So you double the distance, it goes down by a factor of 4, and it behaves the same way as the gravitational force in terms of how it goes with distance. So if you have two protons and you bring them together, gravity is going to pull them together, but electromagnetism is going to push them apart. And you can go and work out the ratio of these two forces. And if you haven't done this, and some of you, if you're physics students, you can work this out pretty easily. You'll find that the electromagnetic repulsion is 36 powers of 10 stronger than the gravitational attraction. So gravity is a very, very weak force compared to electromagnetism. So you're sitting next to someone in your chair, in these two chairs. So can you tell me whether you're pulling on each other gravitationally? Who thinks you're pulling on your neighbor gravitationally? You can put up your hand. Okay, not all of you. Who thinks you're not pulling on your neighbor gravitationally? Okay, so some of you didn't answer either question. What's your answer? Doesn't matter. So what about electromagnetism? Are you pulling on your neighbor electromagnetically? 2 said yes. 3 said yes. Are you pushing on your neighbor electromagnetically? No one's saying anything. Are you not pulling on your neighbor electromagnetically? No opinions. So it kind of depends how you came here and what you did before you came here. If you bicycled in or you combed your hair very vigorously, you've built up some static charge on yourself, and then you can be pulling on your neighbor electromagnetically. But if not, you don't have any unbalanced charge and you're made up of atoms or molecules. Atom is a simple thing that you can talk about in terms of structure of matter. So an atom has a positive nucleus and it has an equally negative electron cloud. And the charge between the positive charge of the nucleus and the negative charge of the electron cloud are balanced. So you're neutral. And so you're not pulling on your neighbor electromagnetically or pushing on your neighbor electromagnetically, but you are pulling on your neighbor gravitationally. And now if you scale this up to, say, 2 stars, they're mostly neutral also, and they're not interacting much with each other electromagnetically. But because they're much, much more massive, they're pulling on each other gravitationally. And then you can scale this up to galaxies. They're much more massive, and gravity is going to be way, way, way more dominant than the electromagnetic force. So when you get to larger and larger scales, matter is neutral. There's not much electromagnetic interaction. Gravity, even though it's a much, much weaker force, becomes dominant. So on the scales of cosmology, we've got to use a model for gravity because that's the dominant force. And the best model we now have for gravity is Einstein's theory of general relativity. So what Einstein did is he came along, and Newton had this picture of physical reality where he had a fixed space, and in this fixed space there was a uniform time that would run, and you could collide balls and study conservation of energy and momentum. And then Einstein realized if these balls were moving at speeds close to the speed of light, you could come up with a better description of reality by allowing your space and your time to participate, and he made space and time dynamical. So that's what the general theory of relativity does. It describes the dynamics of space and time, and I can't really give this to you without using words, but the best description is in terms of the partial differential equations of general relativity and their solution. And I can try to make a crude approximation of what those solutions are doing and say this in words, but these are just words, and so they're going to maybe cause some problems with intuition. So what general relativity does is it kind of wanders around in the universe and it looks for regions of space where there's slightly less mass, and in these regions of space it creates more space, and that space has to go somewhere, and that spreads out, and that's the expansion of the universe. So this is not that easy to appreciate. So I'm going to try to use a few demonstrations here. So what I have here is an elastic band. It's an exercise band, and I've put a wave on it, and it might not be really clear on the slide, but you can see this wave, and it's got peaks and troughs, and it's got a wavelength, and if you've got a meter stick that's held together by electromagnetic force, that's not going to expand because that's on really small scales and gravity is not important. But on larger scales, if the universe expands, then the wavelength gets bigger and the pitch goes down. So if you started out with blue light and let the universe expand, it could become longer wavelength red light. And this is not a very accurate model for what general relativity does. General relativity does not go to the ends of the universe and start pulling. and as far as we know, there are no ends. It goes into space and it creates new space, and that space spreads out. And this also doesn't just happen in one dimension, it happens in all dimensions. And let's move on to another slide here. So this is what I just showed you. So we have a wave here and it has some wavelength, and this we need to characterize the size of the space. So we can think about that as the distance between the two hands, and as time goes on, the distance gets bigger and the wavelength gets stretched. And if you have an elastic sheet, you can draw this, and you can do this at home with a meter stick, and you'll find that the distance between the peaks is proportional to the distance between your hands. If you double this, the wavelength doubles. Excuse me. So this is called redshifting, because you start out with shorter wavelength, bluer light, and then as time goes on, it becomes longer wavelength, red light. And astronomers talk about this in terms of a scale factor, which very loosely you can think of as the distance between the hands. And that's a function of time. So as time goes on, A gets bigger. At earlier times, A is smaller. At later times, it's larger. And astronomers, at least physicists, prefer using the scale factor. Astronomers prefer using the Z, this redshift. And the way this is defined is the scale factor at the present time divided by the scale factor in the past when the light was emitted. So if you have a star here and it emitted light, and that light was going to the right, and as time goes on it'll continue to the right. If you're over here, you'll see that it's redder than when it started out over here. And A has got bigger, so in the past A was smaller. At the present time, A is equal to A now, so A now divided by A now is 1, and 1 plus Z is equal to 1, so Z is equal to 0. At the present time, the redshift is 0. As you go back in the past, this gets smaller, it's in the denominator, so Z gets larger. So in the past, Z is larger, in the present, A is larger if you go towards the present. So this is the expansion of the universe, and this is the guy who first saw this. He didn't realize what he was seeing was the expansion of the universe. This is Slifer, and he used this telescope at Lowell Observatory in Flagstaff, which is about 50 miles south of the Grand Canyon, if you've ever been there. So he was looking at galaxies outside the Milky Way, and he passed the light that he collected here through prisms or diffraction gratings and broke the light up into its spectrum. And he then could identify the atoms that produce that light in these galaxies far away. And he could compare the wavelengths they produced in his lab. And he found in most cases that when he was looking at the atoms in the other galaxies, they were emitting redder or longer wavelength light. So you've probably noticed a very similar effect if you've listened to an ambulance or a fire engine or a police siren. If the engine is coming towards you, the pitch is higher, and as it goes past you, the pitch drops. That's the Doppler effect. And that's the kinematic Doppler effect due to the motion. This is a slightly different Doppler effect. We'll come back to this in a second. But when it's moving towards you, the pitch goes up, so it gets shorter and shorter wavelength. So if you have red light there and it's moving towards you, it becomes bluer. While it's moving away from you, the pitch goes down, so the wavelength's getting bigger. So if it was blue light and it was moving away from you, it would look redder. So Slifer found this red shifting, and he realized these things were moving away from us. What he didn't realize was it was the expansion of the universe. One way to think about this is to think about a firecracker. So if you had an explosion right over here, everything would move away from you. And if you had a way to study how fast those guys were moving, they would all be redshifting, because if it was a spherically symmetric explosion, it would move away. That's not what's happening. What's happening is every point in space is moving away from every other point. And we'll come back to this because it's kind of a little difficult to appreciate. So first of all, I want to talk a little bit about galaxies. So at the present time, the galaxies are like the ping pong balls, and the space between them is the black elastic band. So what's expanding is the space between the galaxies. The galaxies themselves, after they're formed, they're not changing in size. It's just the space between the galaxies that's getting bigger and bigger. And I have a cartoon of that up here. So we have bread here, or cake, and you have chocolate chips in here. And this has got to just be a part. This is a one-dimensional universe because it moves in one dimension. And this is a three-dimensional one because it's got a vertical, three-dimensional space. It's got a vertical axis and two horizontal axes. And so you can kind of think about this. And if you go to the edge and look out, it's going to look very different than when you look inside. So this is not going to be isotropic. So if you want a universe like this, and this is called a flat Euclidean universe, it's got to go out to infinity in all three dimensions. Because if it didn't do that, you'd go to the edge and it would look different when you looked out compared to when you looked in. And the distribution wouldn't look isotropic and it wouldn't agree with the microwave background picture. So here are our galaxies, and we can place our observers on these galaxies, and in principle there's an infinite number of them. It goes out in all three dimensions. And we can place an observer in galaxy 2 and ask her what she sees, and she's going to tell you she sees every galaxy move away from her as the east rises. And we can place an observer on galaxy 3 and ask him what he sees, and he's going to tell you he sees every galaxy move away from him as the east rises. So what Slifer saw was stuff moving away from us, and that doesn't have to mean that he's at the center of an explosion in the past and he's seeing this stuff move away from one point in space. And this is the more correct description of what's going on. Every point in space is moving away from every other point in space. And so if Slifer had a friend on Andromeda and asked her to do the same experiment he did, or she did the same experiment and looked at galaxies outside, away from Andromeda, she would see all the galaxies move away from her also. So any observer at any point in space would see galaxies move away from them, provided they look out on large enough scales. So in here, it's a three-dimensional universe. So you'll have a scale factor for each of these three dimensions, and the volume would go like the cube of the length because it's a cube, and so there'd be three scale factors. The volume would expand in proportion to a cubed. And this is just the uniform expansion. The next step came with Hubble. And what Hubble did is he had a much better telescope than Slifer's. And with his telescope, he could resolve individual stars in these galaxies that Slifer was looking at. And he could see that some of these stars were variable stars, and he was able to identify them. And some of this work had to be corrected later when people better understood these stars. But he could identify them as cepheid variable stars. And those are very, very important stars because of a relation Henrietta Leavitt had found in the early 1900s, I think in 1905 or 1906 or something, maybe it was 1907. So she would get a hold of all these glass plates from observers at these various telescopes across the US. She was based at the Harvard-Smithsonian Center in Cambridge, Massachusetts, and she would have pictures of the same region of the sky, because some astronomers would just take pictures of the same region over and over again to try to see things that were changing in time. And she realized that she could see stars in these pictures that were brightening and dimming, and she identified them as cepheid variable stars. So Polaris is a cepheid variable, and there's an instability in these stars, and they brighten and dim very, very regularly. And she realized by looking at nearby ones that the brightening and dimming, the period of the oscillations, was related to how intrinsically bright they were, related to the wattage of the star. So it's kind of really difficult figuring out the wattage of an object that you're looking at. It could be a very bright object far away or a dim object nearby. And so you've got to have some way of being able to distinguish between those two things. And if you can tell the wattage of the star from the periodicity of the brightening and dimming, you can then use the inverse square law of radiation and figure out the distance. And so Hubble could figure out the periodicity, and so he measured the distance. And that's the distance over here between us and the galaxy he was looking at. And that's the recession speed. And he discovered this very, very, very interesting law. It's called Hubbles Law. It tells you that the speed of recession is proportional to the distance of the galaxy. So if you have a galaxy twice as far away from us, it's moving twice as fast. If you have a galaxy 3 times as far from us, it's moving 3 times as fast. It's a linear law. And I'm starting to run out of time here. So that slope is the Hubble constant, and it's got strange units. I can talk about that later. But this is distance over time, and that's distance. So this has dimensions of 1 over time. So it's roughly 1 over the age of the universe, very loosely. So this is an illustration of the kind of measurements that support Hubble's law. So what we're plotting up here is the speed at which these galaxies move away from us in kilometers a second. So this is 10 to the 4 kilometers a second, 10,000 kilometers a second, 20,000 kilometers a second, and so on. And this is the distance to the galaxies here. You can kind of forget the residuals down here. So 100 megaparsecs is here, 200 is here, 300 is here, and so on. And so if you go to a galaxy that's 100 megaparsecs from us, it's moving away at roughly 7,000 kilometers a second. A galaxy 200 megaparsecs from us is moving away at roughly 14,000 kilometers a second. And this solid line is Hubble's law. And this is the expansion of the universe. So maybe, should I continue for 5 or 10 minutes? Okay. So this is the expansion of the universe. We know the universe is expanding. And we know that observers everywhere else will also see that the universe is expanding. This is kind of quantified into what's known as the cosmological principle, that the universe is spatially isotropic for all cosmological observers. So if you have a friend on Andromeda and ask her what she sees on large scales, she'll see it's also isotropic. So if you kind of think about that, if I'm over here on the Milky Way and I look around and I see it's isotropic on very large scales, and then I move over to Andromeda, which I can't really do, but if I do that as a thought experiment and I look around and it's isotropic on very large scales, so you're seeing that the universe is isotropic from 2 different places in space. And there's a theorem in geometry that tells you that there's a bigger symmetry for a system like that. And that symmetry is called homogeneity. And that again is jargon, but the easy way to think about homogeneity is to think about a big gallon jug of milk or something that's pasteurized and homogenized. And if you put on your scuba suit and swim around inside there, as long as you don't go to the walls, it's going to look exactly the same whiteness no matter where you move in space. And that's got much more symmetry than something that's isotropic about 1 point. And then if you take the simplest topology, there are only 3 possible geometries for space. So we live in a 3-dimensional space. So it's like this room. So there's a vertical dimension and there's 2 horizontal dimensions. But I can't show you, I can't draw these 3-dimensional spaces for the closed and open cases. So I'm going to go down 1 dimension and talk about 2-dimensional spaces. So I'm going to talk about a 2-dimensional flat space like the top of this table. And we've already talked about going to the edge and looking out. So if you look out, it's going to look different than when you look in. So it wouldn't be isotropic. And so the edges would have to go out to infinity, so they don't have any edges. And that would give you an isotropic two-dimensional flat space. And that's like this guy over here. It's a flat space, and it has zero curvature. You can also have a two-dimensional positively curved space like the surface of a football, and you're not going inside the ball, you're not going outside, you're thinking of yourself as a little ant, and you crawl on the surface of the ball. It's a two-dimensional thing because you just need a latitude and a longitude or two angles to specify where you are. And that's, by definition, closed, and it's positively curved. And the opposite of the closed is the open universe, which is negatively curved, and that's like a saddle shape, but again, you've got to get this to go out to infinity. And these guys are the density of matter in the universe, and if we have time in the discussion, we'll talk more about this. But this is density in a different system of units, and I'll try to define it, but this is said to be critical density. It's omega naught is equal to 1. This is lower density, omega naught is less than 1. This is higher density, omega naught is greater than 1. And the scale factor is what describes the expansion of the universe. So an easy way to think about the scale factor is to think of the radius of this two-dimensional sphere, and as time goes on it gets bigger and the radius gets bigger, and this is the scale factor. And now I'm going to put in a couple of equations. So the scale factor's behavior is governed by Einstein's general theory of relativity, and this was first used by Friedman, and so this is sometimes called the Einstein-Friedman equation. But basically, you want to figure out how this changes with time. And you know what's causing gravity is the mass. And if you're talking about an infinite universe, there's an infinite amount of mass. And it's very, very difficult to do mathematics when you have a bunch of infinite quantities. So to make your life simpler, you look at a little patch of space, and you look at the mass in there, and you talk about the mass per unit volume. And that's called the mass density, and that's going to cause a gravitational field near it because physics is local, and so you can do this on small scales and not worry about the whole universe, and you can do all the physics locally. So we'll talk in terms of the mass density and the pressure. So this Hubble constant, or the Hubble parameter, is the rate of change of the expansion. And so what's happening is it's the expansion, sorry, not the rate of change. So you have the scale factor. As time goes on, it gets bigger and bigger. And so you can take it at two different times and measure the difference between them. And that tells you how much it's changed by. And if you divide that distance by the difference in time, that tells you the speed of the expansion. And in physics, that's denoted with a dot on top. So a dot is the speed at which the universe is expanding, and this is the speed divided by the size. So this is the Hubble constant, or it's the Hubble parameter because it changes with time. But we know everything is moving away from us, and so we know things are moving away. So the next obvious question is, does this expansion speed up or slow down? So does the person who's powering the expansion of the universe, does she have her foot on the brake, or does she have her foot on the accelerator? So she could start out expanding, and then if you hit the accelerator, that expansion speeds up, and that's a positive acceleration. But if you hit the brake, you could still be moving away, but it would slow down and slow down and slow down and get to some maximum size, and then eventually stop. And that's what happens when you have deceleration or negative acceleration. And so the easy way to think about this is in terms of an equation. And it's a little bit unfortunate that I have to use an equation, but I want to try to get this through a little bit more technically. And so the equation gives you the acceleration in terms of the force per unit mass, effectively. So this is pretty much Newton's second law, which you've sometimes seen as force is equal to mass times acceleration. You can also write that as acceleration is equal to force divided by the mass. And so the second time derivative, or the second dot, gives you the acceleration. And it's kind of really unfortunate that you use A for acceleration in Newtonian mechanics and also A for the scale factor here. But I'm only talking about the scale factor. And A means the scale factor. A with two dots on top is the acceleration. So the acceleration is caused by the mass and the pressure, and we'll come back to that in a second. And it's all caused by gravity. That's why you have Newton's big G over here. And it's as easy to think about. There's a minus sign over here. Let's just forget all these guys for now. So if you have mass, you have two galaxies, and you have more galaxies. So Einstein comes along and creates space and starts to push those guys apart. But Newton's gravity, which is a pretty good description for what happens between galaxies close by, they're going to pull on each other. And if you have much more mass, they'll overwhelm the space creation process, and they'll stop the expansion of the universe. And so that's what this negative sign is telling us over here. You have a negative sign over here. If you just have mass over here and you have enough of it, A double dot, the acceleration is going to be negative. So even if you start out at the Big Bang and let the universe expand, if you have enough mass there, it's going to stop the expansion. So let's look at this term now. So this is what comes from Einstein's rest mass energy, where you have E equal to mc squared. There's also energy in the form of energy of motion. So you have kinetic energy. And those guys also carry energy. And then Einstein will tell you, because there's an energy associated with that motion, there's also going to be a mass associated with that motion. And because there's a mass associated with that motion, gravity is going to act, because that's going to create a gravitational field. So even if guys are moving around, they're going to create a gravitational field because of the fact they're moving, and not just because of the fact that they have mass. And that's a relativistic effect. If I was not using natural units, there'd be a speed of light squared in the denominator here. So this effect only becomes important when things are moving fast. So this is the pressure, because the pressure, as you kind of compress stuff and get it to move faster and faster, the pressure goes up. Sorry, the pressure is a measure of the kinetic energy of your system. So you have pressure here. So if you have galaxies, they're pulling on each other, they stop the motion, or they're slowing it down. And if those galaxies are also moving, they have more energy, and they slow down the motion even more, and they'll cause a deceleration. And so you're really happy, and you go tell your observer friends that the universe is decelerating. And can they go and measure this? And so they go and measure the acceleration, and they find that it's actually positive and it's not negative. And so you're kind of stuck then. You have two options. You can say Einstein was wrong and this equation is incorrect, and so your prediction of a deceleration was incorrect, and we need a better model for gravity than general relativity. Or you can say that Einstein's general relativity works on the scale of black holes. It works mostly for the cosmic microwave background, and we want to be conservative and we don't want to throw it away. And so how do we fix it up? And we can fix it up by introducing a hypothetical substance, and so this is matter, and then the symbol lambda here is for the cosmological constant. So I've put in a cosmological constant mass density and a cosmological constant pressure. And now I want to try to make this, flip this sign. So the only way I can flip this, I can't flip the sign of 4 or pi or g or 3. I have no control over them. So the only thing I have control over is what I put in my universe, which is in the square parentheses. For matter, I can't flip the sign. You have so much mass per unit volume. It's a positive mass. The pressure is positive. I can't flip the sign over here. But I'm going to introduce a hypothetical substance. And we know from experiments in the lab that we have strange quantum mechanical systems. So one effect is called the Casimir effect, and you can look for that on Google. It's CASIMIR, and it has to do with vacuum fluctuations from the Heisenberg uncertainty principle. Another quantum mechanical effect is the Lamb shift in the hydrogen atom, and that's LAMB. And both of these have to do with zero-point fluctuations. And it turns out that zero-point fluctuations, at least in the lab, can behave as a substance that has negative pressure. And so there's some hope that maybe on cosmological scales, you can introduce a new substance, which we're going to call the cosmological constant, that has negative pressure. And its equation of state is P equal to minus rho. For matter, P is either positive or zero, depending on what kind of matter you're talking about. But P never gets negative for ordinary matter or even for dark matter. And so we can get P for the cosmological constant, which is a hypothetical substance. We don't know for certain that it's there yet. But if you get this to be negative, so rho plus minus 3 rho, the thing in the round parentheses here is going to be minus 2 rho lambda. And if you get rho to be much larger than this, then everything inside the square parentheses can be negative, and you'd have a negative sign here times a negative sign here. That would be a positive, and so you get positive acceleration. And that's what dark energy is. It's this hypothetical substance introduced to make Einstein's theory of relativity consistent with the observations. And if this was just one set of observations, we'd be crazy to introduce dark energy for that. But there's probably almost half a dozen or more observations that give you roughly the same amount of dark energy, and these are independent observations. And so cosmologists think that dark energy is out there. We're only seeing the gravitational effects of dark energy and dark matter. And I think I've pretty much run out of time. And so maybe if there's questions, I'll go over the rest of the slides then.
I have a question that why in some galaxies they saw or they detect dark energy, and some galaxies do not have dark matter?
Okay, so most galaxies that people have looked at seem to have dark matter. And maybe I should just explain why people think they have dark matter. So what we're looking at, so if you look at a spiral galaxy, the stars are moving typically in circular orbits around the center. And it's very similar to what happens in our solar system. If you look at the planets around the sun, they're all in a disk. And Mercury is closest by, and Pluto is far away. So Mercury, because gravity is an inverse square law force, Mercury is close by, and so it's r. The radius from the sun to the Mercury is very small, and that's in the denominator. So the gravitational effect of the sun is really, really strong, and it bends Mercury's orbit a lot. And it makes Mercury go really fast around the sun. It takes about 88 days to go around the sun. But if you go out to Pluto, which is at 40 AU, it takes about 220 years to go out. So if you have a system where you have a big mass at the center and stuff goes around it, as you go further and further out, it takes longer and it moves slower. So you'd expect when you measure the speed of Mercury, it's going to be much faster than the speed of Pluto. And we can do that in our galaxy. And I put this up here as an equation. So what this comes from is just F equal to ma. Have you done some physics? Okay, so you have F equal to ma, and F is an inverse square law force if you have a star moving around the center of the Milky Way. And so then if you have a big M for the mass at the center and a small m for the star, the force is big G times big M times small m over r squared. And if you assume for a second it's a circular orbit, then you can write the acceleration as v squared over r. And that's just this equation here. So it's v squared over r, and that's gm over r squared. And so I multiplied through by r. And so if you have the sun's mass over here, and you take the square root, v should drop like 1 over square root of r as you go from Mercury to Pluto. And you can show this by using Kepler's laws. So you can do the measurements, and you see that the planets obey this really, really well. So if you plot v on this axis and r on this axis, if we do this for the solar system, it would drop like 1 over square root of r. But if we do this for galaxies, and these are 4 different spiral galaxies, the speed rises. So this is the speed over here. It rises and then it flattens out. And it's gone beyond the visible edge of the galaxy. So if I go back to my picture of the Milky Way over here, we can go out even further, okay, over here. So ordinary starlight that we see with our eyes goes out this far. It's roughly a diameter of 160,000 light years. But there's lots of hydrogen gas clouds out here that are also in orbit around the center of the Milky Way. And hydrogen gas emits 21 centimeter radio wavelength. So you can study the motion way outside the visible part of the Milky Way by collecting 21 centimeter radiation. And that's how people go beyond the star edge of a galaxy. They use radio waves, and they see that the speed rises to maybe between 150 to 300 kilometers a second, and then it flattens out. And this is beyond where there's stars. So what that's telling you is that v squared is a constant even at really large distances from the center of the galaxy. It's not dropping like 1 over r. So there's got to be mass here that's increasing as you go out further from the center of the galaxy. But that's not in the form of stars. And so it's not mass that's shining, so it's dark. That's the dark matter. And in almost all galaxies we see this. There's maybe 3 or 4 dwarf galaxies where people have tried to look at, and they apparently find that there's not much dark matter in them. And it's not clear whether that's really correct, the observations are correct, or whether those guys interacted with something and the dark matter got taken out of it. And we don't know for sure, but that's just a handful of galaxies. I mean, almost every one that people have looked at have dark matter.
You mentioned your friend in Galaxy, in Galaxy Andromeda, and she would see the space expanding. But I think just this one galaxy is approaching us, and one day we will collide. Am I right?
That's correct. So I haven't shown you this demonstration. I don't know whether I should try this or.
We can try. So now it will be a bit loud, but don't worry, it's not a time machine or.
So yeah, maybe you can hold this. Can you hold this? So can you hear me? Okay, so this is a two-dimensional positively curved universe. And we have the galaxies on here. They're stuck on here because they're like this. The universe, the space between them is expanding, but the galaxies are not moving. So here you have to think of yourself as a little ant. And if you can imagine this blowing up, the space is going to get bigger and bigger and bigger. And so if you're on this galaxy and you look at light from here, if it starts out blue, it's going to propagate a small distance and it won't cover much of space. And so maybe it starts getting a little bit red, but if it comes from further away, it'll be more red. If it comes from further away, it'll be more red. Excuse me. And that's the expansion of the universe. But as you said, Newton will tell you these guys are attracting each other. And I can't show you that, so it's really correct. These galaxies move towards each other. So when you have galaxies close by, like Andromeda and the Milky Way, their local gravitational attraction is much stronger than Einstein's space creation process. So these guys will be pulled together, and if you look at Andromeda, the way Slifer looked at it, you see that light is blue shifted and not red shifted. But if you get out to large enough distances, Einstein's space creation process is much more effective, and those galaxies are moving apart. So yeah, maybe we should just stop this for now and see if people have more questions. We can run it some more.
So thank you for a nice lecture. I'd like to ask you about the Hubble tension and what's your standpoint on it.
So if we go back, maybe tomorrow is a better place to ask this question. So the Hubble constant is this guy over here. It's the constant of proportionality between the recession speed and the distance. And because astronomers measure the speed in kilometers per second and the distance in megaparsecs, the units it has are kilometers per second per megaparsec. And this is my favorite value. So this is the slope of the Hubble law, and it's a straight line, and this is from older data, and the slope then was 72 kilometers per second per megaparsec. So if you look at this, you can measure this in many different ways, and you can measure this from the microwave background. If you can measure it through local expansion rate measurements where you use Henrietta Leavitt's Cepheid period luminosity relation and use that as measuring distances to type 1a supernovae. So if you do it that way, you end up with about 74. And if you do it with the microwave background, you end up with about 67.5. And so that's what's usually called the Hubble tension. So I think that's more a problem with possibly with the measurements that are made in the local universe, because if you don't use Cepheids and you use tip of the red giant branch, you get about 69 or 69.5 that way. And you use baryon acoustic oscillations, you get about 68 or 69. And you use the WMAP cosmic microwave background measurements, you get about 68 or 69, and you use the Planck ones, you also get about 68 or so. And I think the tension is between different measurements locally of the expansion rate. And the Cepheids seem to prefer a higher value than the tip of the red giant branch. And I think that's what we need to look at more than the tension between the cosmic microwave background and the local measurements. But it'll become clearer in the next 5 years, hopefully.
But since the launch of Hubble telescope, we are doing
James Webb.
James Webb, but since the Hubble, it has improved to about 70, the value.
Yeah.
So,
so this is from the Hubble's, it's Wendy
Yeah,
Friedman's
Wendy,
first plot from 2001. So this was what the Hubble Space Telescope was launched for. One of the reasons to get a more accurate measurement of the Hubble constant. So ever since Hubble's measurement in 1929, this quantity is the most measured quantity in science. There's probably about close to 900 measurements of it, and it still hasn't been completely resolved. So it's somewhere, if you go to the highest local expansion rate measurements, it's about 74. And the microwave background's giving you something like 68.
Yeah, but originally when Hubble determined it, because of this mistake with distance, he got something like 500, right?
Yeah,
so
Hubble got 500. So because he didn't realize that there was, at that point, so people didn't even know there were galaxies outside the Milky Way then. So in 1926, Hubble showed that convincingly through the Cepheid period luminosity relation, that these objects were way outside the Milky Way, and so they had to be external galaxies. And then in 1929, he did the Hubble Law stuff. And there are two different kinds of Cepheids, and that was discovered much later.
Thank you for a very nice presentation.
Thank
My
you.
question is that obviously if the universe is going to expand more, faster, what is going to happen in the future? Because there will not be matter always, because matter will always will decay, because protons will decay. So how that will look like? You probably have some slides about that, right?
Yeah. So I can maybe talk about this for a few minutes. So we looked at this and we saw that it's moving at maybe a few hundred kilometers a second. So this is very, very slow compared to the speed of light. So most of the energy in this kind of matter, the cold dark matter and the ordinary matter, is in the rest mass energy, the mc squared part. And so if you want the energy density from this, which is called the dynamical mass energy density, because you're using dynamical techniques to measure it, it's just the rest mass divided by the volume. And the volume expands with 3 parts of the scale factor. So this drops like 1/a cubed. And if we turn this into more conventional units, it's about 10 to the minus 30 grams per cubic centimeter. So if you look at the density of matter on Earth, you take the Earth and divide it by Earth's mass and divide it by its volume, it's about 5.5 grams per cubic centimeter. So this is about 31 orders of magnitude less dense. So it goes, as time goes on, the universe gets less and less dense. In the past it was more dense. And this is not the proton decay. So this is the guy who kind of started with dark matter. So I haven't really talked much about it, but I'll skip over it. This is the Kobe satellite, and this measured the microwave background for the first time. And it got a very accurate spectrum from this instrument. And I want to show you the spectrum. So this tells you the intensity of the microwave radiation at different wavelengths. And this is at 2 millimeters, 1 millimeter, 2/3 of a millimeter, half a millimeter. So the peak in the intensity is roughly about 1.9 millimeters. And the shape is what's known as a black body shape. And if people want, I can talk more about this later. But once you know this is a black body spectrum, you can figure out its mass density through work that Planck did and Boltzmann did. And what it tells you is that the energy from Boltzmann's relation is the energy of the light is proportional to a constant times its temperature. And also from Planck, it's proportional to 1 over its wavelength. So longer wavelength stuff is cooler because the wavelength is in the denominator. And shorter wavelength stuff is hotter. It'll give you a larger temperature. But we know that wavelength expands as the universe expands. So the energy in this light drops like 1/a. And so if you're getting the energy density or the mass density in the radiation, it's mass divided by volume, but mass is really E over c squared. And E drops like 1/a. And the volume goes like a cubed. So for radiation, this goes like 1/a to the 4th, while for matter, it goes like 1/a cubed. So if we plot these two guys, you can plot the density against the age of the universe. So the scale factor is larger here, the universe is older here, this is where we live. As you go back in time, you go to the baby universe, and the redshift is larger here, the scale factor is larger at this end. So if I plot the mass, it drops like 1/a cubed, which is slower than the radiation, which drops like 1/a to the 4th. And as you said, as time goes on, the mass density drops, the radiation density also drops. But if we have a couple of minutes, we'll talk about the dark energy and how we measure that. And so what we want to look at here is universes with 2 different Hubble laws. So I'm going to plot distance on this axis against recession speed. What I showed you previously had it flipped the other way, but now we have distance on this axis and recession speed here. And I've got a universe that expands slowly and a universe that expands more rapidly. And if we look at a galaxy at the same distance in both these universes, the one in the universe that expands more slowly has a slower speed. This speed is closer to 0 than the speed of the galaxy in the more rapidly expanding universe. And it's kind of interesting to think about what you're looking at here. If you're looking at a galaxy at a distance d, you're not seeing it the way it is now, you're seeing it the way it was in the past. And so if you see a galaxy at a larger distance in this universe, you'll see it as it was further back in the past. And so as you go out to larger and larger distances, you're seeing this further and further in the past. So we have three options. It could be that as you go very, very far away, that the expansion rate remains the same, that it's a straight line. Or it could be that in the past, the universe expanded more rapidly, like the green universe, and then as you got to the present, it slowed down, and that's a decelerating universe. Or it could be that in the past, when you go to further and further distances, that it was expanded more slowly, like the blue universe, and as you came to the present, it accelerated. So this is an accelerating universe, this is a decelerating universe. And it's relatively easy to do this if you have very, very big telescopes and you understand enough about various sources. And in the 1990s, the sources you could see the furthest away were type 1a supernovae, which people think are white dwarf stars with a binary around it, another companion, and the companion accretes matter on the white dwarf, and the white dwarf goes above the Chandrasekhar mass limit, and it explodes. And a star like this can be as bright as a whole galaxy of 100 billion stars, and it could be as bright as that for a couple of weeks or so. So it's an extremely energetic explosion. So you can see them really, really far away in the past. So you just measure them, and you get the speed. And what you find is that this was in the 1997 or so by two groups. The group led by Schmidt and Rees and collaborators at the Harvard-Smithsonian Center, and Perlmutter's group at Berkeley, and they found everything lay in the blue part of the diagram. So it was this that applied, and you have an accelerating universe. And some of you might have seen plots like this, where you look at the amount of energy you have in a cosmological constant and the amount of energy you have in ordinary matter and in dark matter. And if you don't have dark energy or you don't have a cosmological constant, everything should lie along this line. But the supernovae force you up here, and so they're suggesting that there's a pretty strong, a large amount of dark energy. And the cosmological constant is constant. It doesn't change with time. So if you add it in here, it's like this green line. And this plot is a log plot. So you have to be really careful when you're interpreting this. So it looks like that the green line is barely above the blue line here, but it's actually a factor of 3 or so bigger than the blue line. And this is about 1/3 the age of the universe. So, and this is about 2/3 of the age of the universe. So as time goes on, the radiation dominates, the red line's on top, and that red shifts away, then the matter dominates, the dark matter and ordinary matter, and you get decelerated expansion, and then eventually the cosmological constant dominates and you get accelerated expansion. Okay, so now it's not that easy to answer your question, because if you go back maybe 10 billion years ago in the past, and you asked whether you'd be able to measure the presence of a cosmological constant, your measuring devices wouldn't be sensitive enough to do that. And we don't know now whether this green line is completely horizontal or it slightly tilts up. And if it tilts up, then it's probably going to tilt down in the future. So these guys are also going to get redshifted away, and this guy, if it just continues, it's going to dominate, and the expansion is going to accelerate, and it's going to go faster and faster. And then eventually, the only thing that we'll be able to see is our Milky Way and maybe some nearby galaxies if they haven't died. All the other galaxies will be far away, so far away from us that light wouldn't reach us from them. And that doesn't even account for proton decay. So proton decay, the limits now will give it a lifetime much, much longer than this effect.
Yeah, maybe if there is no question, I will ask concerning, so right now, of course, let's say the standard or benchmark model is flat lambda CDM, where dark energy is represented by the Einstein's cosmological constant, like you explained. But with Jim Peebles, the Nobel laureate, you have worked on the first dynamical dark energy model. So is dynamical dark energy your preferred model, or you think it could be dark energy could really be constant?
So like all the observations right now are consistent with it being a constant, but they're not sensitive enough to rule out a weakly varying dynamical dark energy model. And for theoretical reasons, it's really difficult to understand a constant cosmological constant. So if you just look at quantum mechanics and do the calculation from the Heisenberg's uncertainty principle, you'll get 0-point fluctuations that'll give you a cosmological constant. And the value you get is about 120 orders of magnitude bigger than this measured value. And so that's one problem. It's inconsistent quantum mechanically. And we don't know how to tie this to the standard model of particle physics. It would be much simpler to tie it to the standard model of particle physics if this was a dynamical field. And you could introduce something like a scalar field, just like the Higgs field, but this wouldn't be the Higgs field. It would be much, much less massive and interact much more weakly.
So what, from these outstanding cosmological problems that we have tangents, what do you think that James Webb telescope has the potential to answer?
So it has the ability to see supernovae at higher redshift and probably even cepheids and maybe help improve. It'll probably pin down the Hubble constant more accurately than we have it now. And it's also going to see structure formation like galaxies and clusters of galaxies, especially galaxies being formed very, very early on. And that'll also pin down some parameters of the lambda CDM model or whatever the cosmological model is then. Because it's an infrared telescope. The Hubble wasn't. I mean, it had some ability to see some infrared, but this will see it much longer wavelength infrared.
Yes, so if you could explain more about your work that or the problems you have been working on, or in the past or now.
So I'm interested in like extensions of the simplest lambda CDM model where the dark energy is a constant, and in that model usually people, so one thing is you can see that it's a constant here, doesn't change with time. So one thing I'm interested in is to try to see whether this could be slightly varying in time, and the universe is so old, so it could have been much larger in the past, and as time goes on it's much smaller, and so it wouldn't be introducing a brand new energy scale here that's much, much lower than anything else around. The other thing I'm interested in is to try to better measure the geometry of space. So right now it seems that our universe has this geometry, the flat geometry, And as you go out, it goes out to infinity in all 3 dimensions. But for some experiments, like the microwave background experiment, when you look at the data from the Planck satellite, it seems to favor this geometry by itself. And I'm kind of interested in why that microwave background data is favoring the closed geometry a little bit. But when you combine it with other observations and do a joint analysis, it goes back to being flat. So those are the 2 things. And so I build theoretical models. And then I try to, even with Michal, try to come up with different ways to test them. So we started using these quasar BLR observations, trying to measure the radius and then get the absolute luminosity and do another cosmological test that way. And I want to try to develop other cosmological tests, because I think if you can get a dozen different tests and they give you the same constraints, then it's more convincing. So in things like high energy physics, you can go to CERN and you can collide things many times, and you can collect a lot of data. But for cosmology, we only have one universe, and so you want to try to use as many different observational probes as you can to try to measure what model best fits the universe.
Okay, one more here.
You can repeat it. So for your measurements, you are using blazers. So how far they are? What is the setup?
I think the maximum. So we are using so-called not a blazar. So it's broadline region. So the clouds that are moving around supermassive black hole, and for that we are basically using optical band, optical telescopes. So and then we are looking at different broad lines, and so typically for low redshift, like up to 0.7, we are using broad H beta, which is in optical. Then if you go to slightly higher redshift, you have ionized magnesium. And then if you go to the highest redshift we had was recently for 3 times ionized carbon, which is the rest wavelength is at 155 nanometers, but it's redshifted with sources at redshift 2, 3, it goes to optical. So I think the highest redshift we had was about 3 in that case. So, but it's promising, of course. If you go to infrared bands, you can, of course, then probe also higher redshift sources. So in this sense, quasars are present from early universe. So this is the advantage in comparison with supernovae, which are more limited in redshift, right? So this is the idea, and it's alternative probe to more standardized cosmological probes.